All right, so here is the start of the next video. This is going to be, well, let's write. So these are going to be the 5.4 notes right here. This is the start of 5.4. This is basically simplifying radicals. So basically the first couple topics of the sections of this unit dealt mostly with simplifying, exponents, rational exponents. This is going to deal with simplifying radicals, all right? And again, a radical literally is just basically this stuff right here. It's essentially a square root, but it not just be a square root. It might be, like a fourth root here, or a third root there, or something like that. First thing I'm going to do, I'm going to cross out these examples here. We don't use these, so I'm just going to cross those out. Okay, so first thing I'm going to do is I'm just going to write out a list of perfect cubes here. So it's like 1, 8, 27, 64, 125, and that's good there. And then right here, I'm going to list out my perfect fourth roots, which is 1, 16, 3 is 81, 265, and then 625. Okay, so all right, so these are my perfect cubes. And these are my perfect fourth roots, or fourth powers. Now, what I'm trying to do here, so first of all, starting with when we were simplifying with a number inside of it, we're essentially, if it's the third, first off, we look at the root, it's the third root, and then 104. And if we look at the fourth root of 104, it's going to be a pretty ugly looking decimal. So now what we need to do is we need to look for perfect cubes, hence the third power. Anything to the third power is a cube. So so we're looking for perfect cubes that go into 104. And it just so happens that 104 divided by 8, which we have right here, is equal to 13. So what we can do from that, once we know that there's a number that divides this out, we can split this apart and do a little bit of a multiplication here. We're going to do the cube root of 8 times the cube root of 13. Because anytime that I multiply these radicals here, all I do is just multiply the numbers inside. And if I multiply the 8 and the 13, I get back to the 104. I just write this out to make it a little bit easier so I can break it down. So now I'm looking, I got the cube root of 8 and then the cube root of 13. Again, the cube root of 8 is 2, because again, 8 is just equal to 2 cubes, so this is 2. And then I have the cube root of 13. If I look over here, there's no other perfect cubes that simplify that. And the cube root of 13 is a pretty ugly other number as well, so there's nothing else I can do with it. I'm just going to write it down here, right by my 2, and that's going to be it. All right, so moving on to this other example here, we have the fourth root of 144. And again, I'm looking for, now I'm not looking for perfect cubes, but my perfect fourth roots, fourth powers, that is. And I'm looking for a number over here that can divide 144. Now if you look right here, I get 16. Do a little bit of work there. 144 divided by 16 gets you 9. So you can break this up as the square root, not the square root, the fourth root of 16 times the fourth root of 9. If you look over here, fourth root of 16 is going to be 2 again, because again, 2 to the fourth power is 16. Fourth root of 9, there's no other fourth roots over here or fourth powers that I can simplify that out with, so I'm just going to be left with the fourth root of 9 right here, okay? And again, once you get to this point where you can't do anything more to this root right here, then you just are going to rewrite it with this 2 right here that we got from the fourth root 16, okay? So that's basically dealing with numbers there. Now let's start dealing with exponents. Now I have two options that I'm going to show to you, okay? Now, I'm going to show you the grouping option, which is mostly good for small numbers of exponents, which you're going to see here in just a second. And I'm going to show you kind of the break apart method that we kind of did up here. So I got the third root, or the cube root of x to the 14th power. So what I'm going to do with this grouping method is I'm going to take this x to the 14th. This tells me that I have 14 x's, and I'm just going to list them out here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right. Oh, too far. So I got 14 x's there. Now I'm going to find to see how many groups of 3, it's whatever this root is, number is, it's groups of 3 that I can make from these x's here. So I'm going to circle these up. I got 1 group here. I got 2 groups. I got 3 groups. And I got 4 groups with 2 remaining, all right? I can't make a group of 3 with these, okay? So now, since I have a remaining, what I'm going to do is I'm going to draw in my radical with a 3rd root, and the number of x's that I have remaining, I have 2 x's, so that's x squared. I'm going to write that underneath my radical here as x squared. Now, when it comes to stuff on the outside of the radical, I'm going to write my x down, and I'm going to write x to the power of how many groups I was able to get. Not how many x's I got, but how many groups I got. So it was x to the 1, 2, 3, 4 power. We're going to write this as x to the 4th power. All right? So it's x to the 4th power times the cube root of x squared there. All right. Now, that's the grouping method. Now, that works great for, smaller examples. So, like, hey, let's do this one here. So I'm going to kind of wall myself off some room here. So I see I got 3 x's and I got 2 y's, all right? And now this one's a little bit different because now I have 2 variables, but it's still the same process. It's just we're going to kind of put all of these together into one final answer at the end here. So I have 3 x's here, and now this is the square root. So now instead of groups of 3 like I did up here, I want to find groups of 2. Again, square root is the same thing as having the root 2 out here, okay? Now, let's see how many groups of 2 I can do just with my x's, all right? I have 1 group of 2 with my x's with 1 remaining. I can't do anything with that, all right? And then with my y's, I have 2 groups of y's with nothing remaining, okay? Now, I see that I have a remaining, so I'm going to draw myself a radical symbol. I'm going to put the number of x's that I have remaining underneath my radical, which gets me x. And I'm going to put the number of groups of 2 x's that I have on the outside. So it's just going to be x to the 1st power. And then I do the same thing in the same answer, that is, with these y's. I have 2 groups of y's with none remaining. So I'm not going to put any y's underneath the radical here. And I'm going to put y to the 2nd power out here. Oh. Because, again, I had 2 groups of y's from the 4 here, and 2 groups of y's from the 4 y's there, and then I had none remaining. So none went underneath the radical, and I had 2 that I brought outside. Okay? All right. I just erased it just to give myself a little bit more room. If you need to pause it real quick to get the notes down, you can definitely do that. And I'm just going to erase these out here. Just don't worry about these. Now, we're going to kind of show you the other method, the kind of break apart method, okay? So remember that it was essentially from up here, it was, we did some, radical times some other radical, all right? Because remember that these numbers inside here multiply to 144, okay? We can do that with this x to the 27th power so that we can take a x to the 27th, so we can take the 5th root of it. Now, the key is that you need your exponent here to be to the power of, not to the power of 5, excuse me, but be divisible. Divisible by 5, all right? And that's the thing with our exponents. These exponents in here have to be divisible by our roots if we want to do this method, all right? Now, x to the 27th, it's not divisible by 5, but we can break this up. Now, let's remember this. If I do x to the 1st power, this requires a little bit of exponent rules knowledge. If I do x to the 1st power times x to the 2nd, I am just adding these exponents here. Now I can do that with this as well. So I do x to the 5th root here. Now I pick the lowest number, the number that's lower than 27, but the next closest number that's divisible by 5, which is going to be 25. So I can write x to the 25th power, all right? And now since we're multiplying these, sorry about the bell there. Now that we're multiplying these, again, I'm just going to put another x over here. And remember, this and this power have to add up to the 27, all right? And remember, if you do 27, and basically there'd be 2 over here. So now you have x to the 25th power times the 5th root of x to the 2nd power, okay? Because again, if we add these, multiply these together, we're just going to add the exponents to get x to the 27th power. Now, from here, I simplify. I do 5th root of x to the 25th power. What I do is I just divide out the exponents there. So I do 25 divided by whatever the root is. So so my new answer is going to be x to the 25 divided by 5, which is just x to the 5th. And then right here, 5th root of x squared. I can't break that down any further. I can't do anything more with that, so I'm just left with the 5th root of x squared. That is it right there, okay? Okay, so let's work out this example here. And for this one, I'm going to kind of break them up into their own separate 5th roots. You can most definitely do that if that helps you out. Just make sure to combine all your answers at the end there. So starting off with the 5th root of y to the 10th power. Well, if you see that, you know that the 5th root of y to the 10th, that y to the 10th, that 10 is divisible by 5. So I'm just going to do y to the, sorry about this, y to the 10 divided by 5th power, which is just going to be y to the 2nd power. Now, z to the 32nd power, this 32 here, isn't divisible by this 5. So I need to do a little bit more splitting up here. Again, we want a number that's lower than 32, but divisible by 5, the next closest number to 32, which is 30. So I can do the 5th root of z to the 30, excuse me. And then remember, we're just multiplying these z to, and then what other power would go here? It would be 2, because again, we're just multiplying these two. We're basically doing the opposite of multiplying these. We're kind of splitting it up. Z to the 30th times z to the 2nd, that's just going to get me right back over here. So now I'm working with something, I'm kind of making it into something that I can kind of work with. So now it's the 5th root of z to the 30th times 5th root of z squared. 30 is divisible by 5, so we can do z to the 30 divided by 5th power, which is just z to the 6th power, and then multiply by z to the 5th root of z squared. I can't break up z squared any further, and I can't divide 2 by 5, so I'm just going to be left with the 5th root of z squared. And the only other thing I'm going to say here is once you get all of your stuff simplified, combine it all into one answer. So the y to the 2nd and the z to the 6th were on the outside. We're not underneath the radical, so those are going to go outside of our radical here. And then we have the 5th root of z squared. That's going to stay underneath the radical there, okay? All right, let's do a couple quick examples that kind of combine both, numbers and variables. So we got the 4th root of 625 and z to the 12th power. So first off, let's just break these up into their own separate square roots here. We're going to get the 4th root of 625 and the 4th root of z to the 12th. And if you remember our list of perfect fourth powers, 4th root of 625 is just going to get us 5, because again, if we look over here, 5 times 5 times 5 times 5, or 5 to the 4th power, is going to give me 625, okay? And then I have right here the 4th root of z to the 12th. Well, it just looks like that 12 is divisible by my root, which is 4. So now I do 12 divided by whatever my root is, 12, so it's going to be z to the 12 divided by 4th power, which is just z to the 3rd power. I have nothing remaining underneath my radicals. Everything comes out outside of it. And then let's do this one, and this will be the last example, and then we'll make the next video. So it's the 5th root of 32 times m to the 5th power times n to the 30th. Again, I'm going to break it up as the 5th root of 32, 5th root of m to the 5th, and then the 5th root of n to the 30. 5th root of 32 is going to be 2 as well, because if I do 2 to the 5th power, that's just going to give me 32. I have m to the 5th power, and that 5 is divisible by my root, which is 5, so it's going to be m to the 5 divided by 5 power, which is just m to the 1st power, or just m, and then n to the 30th power, the 5th root of that. This 30th power is divisible by 5, so it's going to be n to the 30 divided by 5th 5 power, which is going to be n to the 6th power. All right. So that's where I'm going to end it for that video.